Hello everyone, welcome back. If you are new, this is a new series that we have started in which we are trying to dissect segment trees from scratch. We already have 9 different videos in this series in which we have discussed how to build segment trees, how to do point updates and range queries. We also discussed the complexity analysis of each of these methods along with their proofs and the entire code walkthrough. And then we solved problems of various difficulties on this range queries and point update itself. And then we discussed, or then we looked at how segment tree structure is very similar to how we proceed with binary search. So we looked at how to do binary search directly using segment trees, and finally we looked at what merge sort tree is and when it is used. So this there is a complete sheet with all the videos and the different practice problems based on the topics that we discussed. If you are new to segment trees or you have basic understanding of segment trees, I would encourage you to solve all the problems in this sheet, and I'm very sure you will be able to grasp a very good understanding of segment trees. So in the previous video we have started with merge sort tree and we have discussed what is merge sort tree, why it exists, and what problem it solves. So in this particular video we will be looking at, or we'll be solving different problems based on merge sort tree. So if you haven't watched the previous video, I would strongly encourage you to watch that particular video before moving ahead with this particular video. So in particular, we'll be solving this particular problem, KQuery of Spodge, and I will also give you hint about the second problem, which is giveaway. Uh, this problem is exactly similar to the first problem that we are solving today, and there is just one difference which we'll be discussing at the end of the video. So with that, let's get started. So let's start with a quick recap of what we have discussed in the previous video. Again, this is just a quick recap. If you haven't watched the previous video, I would still encourage you to watch that. I will link that somewhere in the description on top right section. So this is how a usual segment tree would look like. So you have an array, let's say 14212304. You will all the leaf node will contain the elements of the array. So 0th position will be at leaf node of 0 comma 0, first position will be at leaf node of 1 comma 1, and so on. And each of these non-leaf node will contain the aggregates of their children. For example, in this case we are like aggregate here is sum, so we are maintaining the sum of the children. So 1 plus 4 5, 2 plus 1 3, and so on and so forth. And finally we can query something on this segment tree based on the aggregates that we have chosen, right? Now what is the disadvantage here? The disadvantage lies in the fact that we have aggregated the values. So this 8 denotes that everything in the range 0 to 3, if you sum them all up, you will get 8. But it doesn't denote what exactly will form 8. So there are various different ways to form 8, right? 2 plus 2 plus 2 plus 2 is 8, and similarly 1 plus 3 plus 2 plus 2 plus is also 8. So this doesn't denote the actual element. So actual element data is lost if you look at this node itself, and that's exactly where merge sort tree will help. So this is how the merge sort tree of the corresponding structure would look like. In particular, like we'll have an array, right, and each element will be present in the leaf node as usual. Now instead of maintaining an aggregate, we will maintain the complete array itself. So instead of saying that 1 plus 4 is 5 and maintaining a 5 here, we are maintaining 1 and 4 both. Similarly, instead of maintaining 2 plus 1 or any aggregate of 2 plus 1, we are maintaining 2 and 1 itself, right? So this is the general idea of merge sort tree, and in the previous video we have discussed completely about what is the time complexity and space complexity of building and maintaining this tree. So check that out. Let's start with the problem of this particular video, which is KQuery. The problem is very straightforward. It says that you are given an array of numbers and you have to answer k queries. So the query is defined by a triplet I comma j comma k, where you need to return the number of elements greater than k in the subsequence ai to aj, right? So in the array ai to aj, you have to return how many elements are there which are greater than the given k, and constraints are usual, like 3 raised to 10 to the power 4 and 2 raised to the 10 to the power 5 is the number of queries that we have, right? So how to solve this? So notice that number of queries are very huge, right? So you have just like, you can't do q into n solution for sure, right? Because q into n solution would be straightforward. You can just iterate over it and figure out which all elements are greater than k and increment the answer accordingly. So you can't do that. Instead, you have to do something smarter, and you just have two choice. First choice is, because number of queries are large, first choice can be you process the queries in certain order and figure out a way to optimize along the way, right? So because you already know all the queries in advance, these all queries are given to you in advance, you already know all the queries, you can process the query in some order such that you optimize on iterating over the array again and again. And if you can do that, then you can actually solve the problem in lesser time complexity. So of this method is called offline querying, because what you are saying is, I will take all the queries, like sort them in certain order, and then figure out the answer. So this problem can be solved using offline method, using a square root decomposition, but as we haven't discussed that yet, let's park that solution. And second method is online, wherein you will get one query, you will answer that, then you will get another query, you will answer that, and so on and so forth. So basically, you don't need to have all the queries in advance. So if you just want to understand what an offline query process looks like, there is a very nice video that we have recorded previously, which is maximum sum queries. This is a lead code problem. I would link the video as well as the problem in the description down below. In this particular video, we have discussed how to utilize offline queries. Okay, so with that, in this particular video, we'll be looking at an online query method, because we are looking at merge sort tree, right? Now, the problem states that you have to find out the number of elements greater than k in this particular range, right? So you need to use some kind of range query data structure. So let's say you build a segment tree here. So first of all, a usual segment tree where you have aggregated things will not work. Why? Because let's say instead of maintaining 2 and 1, you have maintained 3 or some other aggregation, and 5 some other aggregation, and so on and so forth. You will not be able to answer how many elements are there which are greater than k. You need this thing, right? To answer number of elements greater than k, you actually need to have all the elements with you. Otherwise, you can't answer, right? So that's where we have to use merge sort tree here, because each element is something which will be required to answer a particular query, right? So hope this point is clear why merge sort tree is required. Now, once we figure out that we need to use merge sort tree, we need to just do two simple things. First, figure out what is the answer for a single node. Let's say you have to figure out the answer for range 0, 3. So you come to this node and you want to figure out how many elements are there which are greater than k. Let's say k is 2. So you have to figure out how many elements are there which are greater than 2. If you are able to figure this out for a single node, then you have to figure out how to merge the values of two nodes. Let's say you know that there are 5 elements which are greater than k here, or let's take a good example. Let's say there are 3 elements greater than k here, and similarly there are 2 elements, let's say, greater than k here, and you want to find the number of elements greater than k in combined these two, right? So how will you merge these two values? So in this particular problem, the merging part is very straightforward. We know that we need to find out total number of elements greater than k. So if we know that number of elements greater than k in the left side is 3, number of elements greater than k in the right side is 2. So total number of elements which is greater than k would be 3 plus 2, 5. So second part, merging the result, is very straightforward here. We don't need to worry about this. We need to worry about how to figure out number of elements greater than k in a single node. So you have maintained the array. So see 1 4 2 1 2 3 0 4. Now 1 4 2 1 2 3 0 4 and the complete array. Now you have this array. You have to figure out the number of elements greater than k in this particular array. How will you figure out? I would encourage you to, like, this is very straightforward problem, and you will do it exactly the same way in which you will do it on an array. So let's say you are given an array and you have to figure out number of elements greater than k in a particular array. Let's say this is the array itself, and you have to figure out number of elements greater than 2 here, for example. So what you will do, you will simply say, okay, one approach could be to iterate over the entire array, but that's what we don't want, right? We will instead say that, okay, we will sort the array and do binary search, right? So let's say you sorted the array and sorted array comes at 1 1 2 4. You can say I can do binary search and figure out where the first element which is greater than equals to 2. So first element which is greater than equals to 2 is 2. So you will say there are 2 elements which are greater than equals to 2, right? So this is what we need to do. At each node, instead of maintaining the original array, we'll maintain the sorted version of the original array. So we know that in 0 to 3, 1 4 2 1 are the elements. Instead of storing 1 4 2 1, we will store 1 1 2 4, so that we can query the number of elements greater than k efficiently, right? So this segment tree or this merge sort tree would be transformed into something like this, where this is exactly similar to the previous one, just that we have sorted each of the array, right? Now let's just take one example and just try to answer that to see how the algorithm will work. So let's say we have to answer 252. Basically we need to figure out how many elements are there which are greater than 2 in the range 2 comma 5, right? So k is 2 and I and j is 2 comma 5. Now as usual in segment tree, the current will start from the root. The root denotes 0 comma 7. So 0 comma 7 overlaps with 2 comma 5, but it doesn't completely overlap, so we will go in both left and right? Now we reach here again 0 comma 3. 0 comma 3 overlaps with 2 comma 5, but not completely overlap, so we will again go to the left and right both, right? So let's just try to go the left. In left it is 0 comma 1. So 0 comma 1 lies outside of 2 comma 5, right? So after 1 2 lies, so 0 comma 1 is completely outside. So basically we don't want to consider this range at all. So what will you return from here? You have to return the number of elements which is greater than equals to k. So you don't want to consider anything here, so you will just simply return 0 from here, right? Now let's come to the right. In the right, 2 comma 3 completely overlaps with 2 comma 5, right? Because it completely overlaps, you will simply figure out the answer in this node. So now what you need to figure out? You need to figure out number of elements which is greater than 2. So how many elements are there which are greater than 2? 0, right? We will say, okay, I will figure out the first element which is greater than 2, or basically this is a sorted array, right? You can simply do upper bound on 2 or lower bound on 3. Both will work, and you will see that, okay, upper bound of 2 is coming as outside of the array. So number of elements which is greater than 2 is 0. So from here as well you are returning 0. Now you got the answer from both left and right. So from here you will just simply add them all up and return back 0. Now we come to the right. 4 comma 7. 4 comma 7 overlaps with this, but not completely overlaps, so we'll go in both the direction. Now let's go to the left. Left 4 comma 5. 4 comma 5 completely overlaps here, right? Because it completely overlaps, we will not go further and we will just take this array and try to answer the query. What is the query? Number of elements greater than 2. So number of elements greater than 2, again you will do a lower bound or upper bound, whatever you want to do, and you will figure out, okay, number of elements greater than 2 is 1, right? And from the right side, 6 comma 7 is completely outside of this range 2 comma 5, so you will simply return 0 from here. Now from this node you will simply return 1 plus 0, which is 1, and finally you are getting 0 from the left, 1 from the right. From the root you will return 1. So basically the answer for this particular query is 1. So hope you got the intuition how the algorithm is working. Now let's quickly discuss the time and space complexity of each of the different methods involved here. So there are two things, right? First, you need to build this merge sort tree itself, and second, the time required to query. There is no update here, so that part we can skip completely. Now, let's talk about the building part first. We need to build this segment tree, build this merge sort tree. Now, as discussed in the previous video, the space complexity would be order n log n, right? Just to reiterate over the uh, fact, what we are doing, we are saying that there are total log n levels, right, in the segment tree, and at each level we are maintaining the entire array, or we are storing the entire array, or in by dividing it into independent subarrays. So 0, 3 is independent subarray, 4, 7 is an independent subarray, and similarly the entire subarray is divided into 0, 1, 2, 3, 4, 5, and 6, 7. So because we have divided the entire subarray into independent subarray at each level we will be storing n elements, right? And there are total log n number of levels, so total space complexity would be n log n to store this segment tree or merge sort tree. Now, what is the time complexity of building this entire thing? Again, same process. Let's say you have to build this entire thing. You will take just order n log n time. But remember, we have to sort it as well, right? So this n log n time would be sufficient to build this particular tree, where you are just storing the elements in the order. But you have to sort each of these individual arrays as well, right? Now, what will be the complexity? I would encourage you to pause and try to think once by yourself. So the complexity would be again straightforward. What you are saying is you are sorting n1 elements and then n2 elements. So it will take n1 log n1, it will take n2 log n2. So let's just write it down. n1 log n1, right? And the second one will take n2 log n2. Assuming that the first one has n1 number of elements and second one has n2 number of elements. Now, if you think about it, n1 plus n2 is equals to n, right? Now we can simply replace this n with n1 with n, and n2 with n without the loss of generality, because log of n1 will anyways be smaller than log of n, right? Because n is greater than n1. So because that's true, now what is the if you take the complexity would be n1 plus n2 log n, which is n log n. So at each level you are requiring order of n log n time. Again, notice that this is not completely n log n. This log n we got, we kind of over substituted the value here. It was n1 log n1, but we have made it log n for simplicity of the computation. So at each level you are requiring n log n time. And how many levels are there? Log n. So overall time complexity to build this entire thing is n log square n, right? Now, there is a way to build this entire thing in n log n as well. How? This is something we will discuss. Basically, you can see this entire structure as simple merge sort, right? How you do merge sort is exactly similar to that. You are merging two arrays into a sorted array above, right? So these two are already sorted, right? And you are merging two sorted arrays and creating the upper array. So because of how merge sort will work, instead of actually sorting this entire thing here, you can take the help of sorted arrays and merge these two sorted arrays in just order n time. So this order n log square n can be reduced to order n log n easily. But yeah, that's an optimization that might not be required in this particular problem, right? Now, we discussed about this is the time to build a segment tree, and this is the space complexity to build this particular segment tree. Now, what about querying? So what we are doing, first of all, this L comma R, how many nodes will be there in this L comma R? Log n number of nodes, right? Why log n number of nodes? This we have discussed in the very first video of this series, in which we have tried to prove the complexity of query is log n. So why the complexity is log n? Because we are actually querying log n number of nodes. Now because we are querying log n number of nodes, it means we have log n of these, right? Now it means we are doing binary search log n number of times, right? So we are querying log n like this query will be a merge of log n number of nodes, right? And because it is a merge, or it is sum of log n number of nodes, in each node you are doing a binary search. So in total you will be doing binary search log n number of times, and each binary search takes log n time, right? Not exactly n again. This n will be the worst case. It will be n1 or n2 based on the level you are searching at. But in worst case, this will be the time complexity of a single query, right? Again, just to reiterate this part, if you remember for 2 comma 5, we said like we have to do binary search over this and this, right? So in worst case, for any query, you have to you will be taking the binary search over log n nodes, and because each binary search would take log n time, total time complexity is log square n for a single query, right? So this is the overall time complexity, assuming there are q number of queries. So q log square n plus n log n. Now I would strongly encourage you to pause the video right away and try to code this entire solution and get it accepted in Spoj as well, because that part is very important. Next, we're looking at the code. So the code is very straightforward. What we have done, we have built the array, the given initial array in the problem. Then we have built the segment tree. We'll look at the segment tree, like in this constructor itself, we have built the merge sort tree. And then we took the query one by one and answer it one by one. So note, we are answering each query at a time or at the given instance. So this is an online mode of query. Basically, even though the queries are known to us beforehand, it doesn't matter. Even if like there are there are some problems which may ask you that, okay, if you have, let's say the answer of first query is 5, so the second query would be dependent on the first query, the answer of the first query. So it may say that instead of giving you ijk for all the q queries, it might give you some generator which with which you can generate the queries based on the answer for the previous queries. So that's something can be possible, and if that is the problem, you are forced to use online data structure. Any kind of offline data structure would not work there, right? So that's a different topic, but uh, this is what we are doing, and we are doing it online because we are answering query one by one without dependent on what the next query is. Now let's look at the segment tree. Segment tree constructor has the first thing is 4 into n, because we know that in worst case the total number of nodes in the segment tree could be 2 into the next power of 2 which comes next to the n. So basically we take it 4 into n, and then we build the segment tree or merge sort tree with the given array, right? And finally the query is simple. We'll call the query based on given xyk and with 0 n minus 1 0. So what is this? I hope you are now familiar with this. This is LRI. We are storing the segment tree in a array. So previously in an array where I denotes the position where this particular L comma R will be stored. So at each node we are maintaining L comma R, the current range that it denotes, and an I which denotes the position where it is stored in the segment tree, right? Now what we are doing in the build method, we are simply looking at the base, like this is the base condition. Basically in the base if you are at the leaf, there will be a single node, and single node would be equals to the value at the value at the position in the array, right? Now once that is answered, you will try to build the segment tree for left and right, this simple segment tree stuff, and then you will merge them. Now this merge can be implemented in two different ways. Either you can implement it in the merge sort way, wherein you know that the left child and the right child will be sorted, and you can just use that to build the current one in order n time. Otherwise you can simply say, okay, I know that this I denotes the range L to R. I will simply iterate over L to R get all the elements in this array and sort it. That is also possible. It's just that you will be having extra log n complexity while building the segment tree, and that is fine. That will also pass the given time constraint. So in this particular solution, I have just done the merge function, which is taking in the two array left and right. Again, notice that this left and right would already be sorted because we have finished processing these two things, and we have said that in segment tree or in the merge sort tree, each node will contain the sorted version. So these two are already sorted, and because they are already sorted, you can simply merge them by using the two pointer approach. Once that is merged, you can simply return the result. Right now, finally, the query method. The query method is again very straightforward. If the node it lies completely outside of the given range, so x comma y is the range that we are querying for. So if it is completely outside of the current range L to R, we know that will not this node or any of the node below will not be contributing to the answer, so we'll simply return 0. Otherwise, if this node completely lies within the range, then we will do a upper bound on k or lower bound on k plus 1 and figure out how many elements are there which are greater than the given k. Otherwise, we need to go both left and right. So we have done that. We will simply figure out the mid and we'll go both left and right and sum the answer for left and right. So hope this entire solution makes sense. If you have any doubts in any of the piece, feel free to post them in the comment section below. I would be able to answer. Now, let's look at the second problem, which is giveaway. So this problem is also exactly similar to the previous problem in the sense that it also asks that you are given an array of n integers and a set of q queries. Each query will be of the form a comma b comma c, where you have to return the number of elements in the range a to b which is greater than or equals to c. So exactly same query. Only difference is here you have an update as well. In the previous problem, this KQuery, we don't have an update at all. So here it is saying that it may ask you to update one particular element of the array as well. Now, because these two can be intermixed, like you may have some update and then some query and then some update and some query, you need to process this update online as well. Now, this problem in particular can be solved in a easier manner using the offline approach, basically square root decomposition, but it can be solved in very similar way using merge sort tree as well. So let's really discuss this the intuition here. Now, only thing here that changes is you need to update the element as well. So let's say a query comes that update this 4 to 5, the element at 4 to 5. So you are updating 2 to 5. So what will change because of this? Because of this, this particular 2 will change to 5, right? Now, as soon as this will change to 5, the ordering change. So you have to sort it again, right? Either you have to sort it or you have to just merge it, right? So both, either you take order n time or you take order n log n time, but order n time is required, right? Similarly, here also as well, this 2 is changed to 5. So because this 2 is changed to 5, the ordering is now different. So you have to again sort it, right? And finally, this 2 is changed to 5 as well. So again, ordering is different. So up till this is true, after this it will be 3, 4, 4, 5, right? Now, what is the time complexity of this update? Time complexity is, as you can see, it will take order and time to update, because what you are doing, you are iterating over all the elements again. So you are instead of just updating one thing, you are merging the arrays again because you know the order has changed, right? So because of this, the time complexity of doing an update is order n. So even though query is log n or log square n, the update is order n. So overall time complexity would still be order q into n, which will not pass the given time constraint because q and n as usual is very huge, right? Now, how to actually solve this? Notice that you can say, okay, instead of maintaining a vector here, how about maintaining a set? So let's say you maintained a set. So if you maintained a set, this update part will be simple, right? So set is already sorted, so you don't need to worry about that. You can simply go and say that okay, erase 2 and add 5. This part is login. Erase 2, add 5, login. Erase 2, add 5, login. So set will take care of the internal sorting by itself. So now the update part is login. That is good. So not actually login, it's log square n, because what you're doing, you're doing an insert in a set at each level, and there are total login levels, and at each level you're doing an insert in the set which will take login time. So order log square n is the time complexity at a given level for updating. Now what is the time complexity for querying? In a set, can you figure out how many elements are there which are greater than k? In usual set you can't, right? That's where either you can code your own AVL tree. I would strongly encourage you to think about how AVL tree. So set is nothing but a balanced binary search tree, right? And balanced binary search tree is red black tree or AVL tree, the well-known two. Now you can think how AVL, you can use AVL tree to figure out this particular problem, that how a given a k, figure out how many elements are there which are greater than k. So you will be able to solve that with an just extra variable in the node of the AVL tree. But you will not want to code AVL tree from scratch for this particular problem. So there is a shorter way out, which is ordered set or policy based data structure. So there is a nice code forces article about policy based data structure. In short, what it is, it basically gives you a tree or a ordered set, and ordered set can also find the order of a key or the actual order of the key itself. So number of elements which are greater than or less than a particular element can be found using this ordered set or policy based data structure. So you can simply replace your original set with a ordered set and everything would work as is. So the updates is log square n, and the queries will still be log square n because of that policy based data structure. So I would encourage you to code this entire solution by yourself. The query part would stay as is. Only thing that would change in the code is this vector would now become a ordered set, and you need to change some of the upper bound and lower bound stuff here and there. That's it. So code this particular solution yourself. I am not 100% sure. Okay, yeah, it's very small. Q is very small, so it should pass actually. Now next, let's look at final problem, which is maximum sum queries. We'll not be discussing the solution of this particular problem. We already have discussed the solution using merge sort tree in this particular video, starting at timestamp I think 12:06. I will link this video. You can watch this video and again try to code and get this submitted in lead code as well. If you face any difficulties and if there are enough demands, I would start the next video from this particular solution. Otherwise, in the next video, we'll be looking at mkth num, which is a very interesting problem and a very interesting application of this merge sort tree. So hope you enjoy the video. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.